Hey everyone, welcome to yet another episode of Vision Language Modeling Series. This is Season 1, Episode 2, and I'm Prithvi. I would like to start with some gratitude. The kind of love, warmth, and support you guys have been sending me for the last couple of weeks has been nothing short of overwhelming, and thank you very much for that, guys. It means a lot. And for those who are tuning in for the first time into today's episode, thanks for dropping by, and I strongly encourage you to go back and check out our back catalog videos because we usually demonstrate the fact that we are building on top of the ideas we have discussed in the previous episodes. So you will have some kind of continuity. With that said, let's get into today's episode. All right, let's look at some code. But before that, let me just start by saying that we are going to look at something called gated fusion networks for modality attention and selection. It sounds like quite a mouthful. So let's start with why learn gated fusion networks and what is the motivation for learning such a technique, right? So it's the question can be easily answered. So let's step back and understand what we did in visual question answering, right? When we try to make predictions or find out the answers for the visual questions, as you can see, the question pertains to the image and the image pertains to the question. You can never answer the questions just with the image or just with the question. You have to combine the question as well as the image to make predictions or to get the answers, right? So that means the contribution to the predictive power of the model comes from both the modalities, and it's an equal contribution. But that may not be the case for all the tasks. Now, what do I mean by that? Let me explain, right? So, unlike visual question answering, there could be certain tasks in vision language space which might have contributions coming from either of the modalities or both the modalities. So, as we are demonstrating in the three scenarios, scenario A, scenario B, and scenario C, there could be a task where the predictive power of the model is purely learned for certain samples in the task from the vision modality, for certain samples the language modality, or it could be both the modalities like visual question answering. But the challenge is, how do you make a single model to adaptively pick and choose modalities, and that is either modality or both the modality. So what we are demanding the model basically is to learn a trick to adaptively pick and choose modalities, right? So anybody who has done some work with gating mechanisms or any kind of work in the past with RNNs or gated architectures like LSTMs or GRUs can immediately realize the fact that gate is the best way to teach that kind of trick to the model, right? So hence the name gated fusion network. So we are basically adding a gating mechanism on top of the fusion technique to make sure that the model has some kind of adaptability when it comes to choosing the modality is concerned. That's all there is to it, guys. It's not at all complicated. Even if you guys have not done any work with GRUs or LSTMs, so the whole gating mechanism is completely new to you, do not worry, and everything will be very clear as we move forward, right? So the next question that pops into your head is, all right, on paper the gating mechanism and the gated fusion network sounds like a neat trick, right? But what kind of practical real world task calls for a gated fusion network? Or is this some kind of a contrived make-believe technique for some hypothetical problems? It's a fair question for anybody to ask, right? So for answering this question, the best way is to give you an example. I'll give some example, give some backgrounds, and move forward by answering this question, right? Are there real world practical problems to solve using gated fusion network? That's the question. And the background is, I'm a movie buff and a big fan of popular platforms like IMDb, and the fact that they are organizing movies across cultures, languages, and countries, and how they are tagging movies into different genres has always fascinated me. So I always seen that as a technical problem, and I wanted to pick the brains of the LinkedIn family. Hence, I asked our LinkedIn family and community as to how do they think that they can approach this problem, and why they approach the problem in terms of justification, right? So ask this question. So to my surprise, the comment section was absolutely on fire. There are plenty of different answers, but my key takeaway is everybody understood the complexity of the problem. That means nobody underplayed the complexity, but everybody overplayed the approach and solution, right? Now, what do I mean by that is full marks to the creativity, but not so much for the practicality, because problems are given and solutions are supposed to be adaptable, applicable, and deployable, right? So in that sense, the signal to noise ratio is not great. I'm not complaining, I'm just giving you feedback. But one answer caught my attention, and I'm calling it as the best answer, and I'll tell you quickly what the answer spoke about, why it is the best answer, and you will understand how it fits into the narrative of this particular episode in a couple of minutes, right? The three reasons why I like this answer is they kept it simple, they thought through the problem deeply, and they have neither underplayed the complexity nor overplayed the solution part of it, right? As you can see, they have framed it as a multi-label classification problem, but what is more impressive about the approach or their solution part is they have realized that tagging a movie can be a little complicated because certain genres or tags are amenable to the vision modality, that is the poster of the movie or the trailer of the movie or the movie itself, right? And then certain genres or tags are amenable to the text part of the movie, like the plot lines or categorical variables and things like that. And they are also smart enough to understand that certain genres are not amenable to either of the modalities. So now you see, right, not only not this answer is impressive, and it is how it is nicely dovetailing and tying back to the narrative of gated fusion networks. So this almost looks like a tailor-made problem for gated fusion networks, right? To the cherry on the top is this person is a master's student, and the girl has really nailed the solution. I have responded immediately, as you can see, right? So now that we know the motivation for learning gated fusion network and also a canonical problem for using along with gated fusion networks to demonstrate the power of gated fusion network, right? So now what is the next question that pops into your head? So alright, so what do I have to do to get a data set? Do I have to scrape or do I have to source? What should I do, right? So fortunately you don't have to do anything like that. We can get our hands on a real world actively researched multimodal data set called MMIMDB, and obviously the MM stands for multimodal. So let's do a couple of things. We'll start with the logistics and then look at the structure of the data set, and then we'll move on to do some analysis and EDA and so on and so forth. So first things first, I've given the link to the data set. Feel free to download and play around. That is the logistics part. And the second part is, let's look at the structure, right? How they have structured is, for each movie we have a pair of files. One is a JPEG file which actually shows the commercial or the poster of the movie that they used, right? And then there is a JSON file to go along with it, which contains all kinds of information, like it could be plot lines or the title of the movie, the cast of the movie, the color, year of release, rating, blah blah blah. There is a bunch of things. We may not need all of those, but I'm just showing you what is available for you to use. Now that we know the structure of the data set, so what does success look like? The success is pretty simple. We will be given a vision side and a text side of things for us as far as the movie is concerned. It could be the plot line or it could be the variable of a feature of your interest. And our goal is to use them some way, shape or form to tag the movie into one or more genres. That's all there is to it, guys. I've given you a couple of examples. As you can see, this is a pretty old movie. This is the commercial poster, and then there is the plot line, right? Another important aspect you want to keep in mind is all the posters may not be in English, and here is an example of a poster which has text in French, but IMDb has done a good job in terms of translating the plot lines in English. So all the plot lines will be in English no matter what the language of the movie is, and you just have to use them. So that wraps up our motivation part and the data set part. So let's try and go to the next logical step, which is our examining the data set and doing some EDA. Alright, let's look at the data set. As you can see, the data set has got 23 golden labels. The labels are nothing but the tags or the genres of the movie, and I've given you a table that reflects the split of data per label between the train, dev and the test set. One of the interesting things that you can notice is there is a sort of imbalance between the number of samples that is available for different genres we see. This could be either seen as an imbalance in the data set, or it could be seen as a reflection or accurate reflection of the real world itself, because in real world usually there will be more romance and thriller movies compared to sport or short or film noir, right? So either way, it's just information for us. If we can factor this in our modeling, that'll be great, right? And a couple of other things I want to cover as far as the data set is concerned is I have a feeling that this is a sort of an AI hard problem. Let me justify with some of my observations. Even though we maintained and observed a couple of things, like there are certain genres the vision modality can nicely signal, and there are certain genres that the text modality can nicely signal. But there are certain genres neither the vision modality nor the text modality can clearly signal, like film noir, short, or it can get confused. And also, to add insult to injury, short and film noir all three has a very low volume in terms of the data set, right? And also, if you look at it, the other aspect is the data set and the labels are not coarse grained, they are very, very fine grained. So for instance, you need to build a model that needs to tell apart romance from comedy or drama, and thriller from mystery, because sometimes it is very hard for humans, even humans, to conflate. So that means there could be some labeling issues also in this problem, right? So all in all, it looks like an AI hard problem. Those are my justifications and observations. And just to give an information for you, there is a co-occurrence matrix of labels. So it gives you an idea as to what are the labels which co-occur in this data set. So the next logical step is where I parse the JSON files of individual movies and pick up the text, the variables that belong to the text modality, right? So it's pretty straightforward. I would request you to go through it. The key things that you want to pay attention is the plot lines. It's an array and there are multiple plots. I wanted to pick the longest one for the better representation of the movie. That's what I'm doing here. The other thing that you want to notice is the list of variables which I found interesting to be used in the modeling process. Actually, I'm not using all the variables that I'm showing here. It's only a subset of it, but feel free to use the variables which you find interesting. Third one is you don't have to split the test data. I mean, it's not important. It's like you don't have to come up with your own split. What constitutes the test data set is given by the data set itself. So with that, I formed the data sets required for modeling, that is the train, eval, and test. You can see the number of samples in each of the data frames, and next cell shows you a nice preview of the data set itself, which is nicely primed for a multi-label classification problem. The next couple of cells are optional. I'm not going to go through that. If you're going to do EDA, feel free to play with the data. One thing that you might want to do is the distribution of the length of the plots, right? So which is an important text feature. The next logical step is critical actually. This is where we pick and choose the vision and language feature backbones. It is not a fixed formula as to, there is no fixed logic as to how do you pick feature backbones for vision and language modalities. It is very much an experiment. I am going with my hunch and picking and choosing certain specific models. You can try, and my choice for vision backbone is a clip model, because I have a feeling that a model which has been fine-tuned to understand similar images and text has a better shot at learning the movies, a better shot at mapping movies with the respective genres. And for the text backbone, I've picked the best sentence similarity model that is available out there. By default, the sentence transformer model that is out there. The sentence transformer model, by default, if you load it, the pooling model that is used is a mean pooling. But you have a choice to pick from mean pooling or a CLS pooling or a max pooling. I am going with the CLS pooling. If you ask why, mean pooling, I've observed, generally does not work really well with the discriminative task. And don't take my words at face value, feel free to experiment. And obviously we are trying to freeze both the vision and the text modalities here. The text and vision and the text backbones. So that means we are not fine tuning the actual foundation model, right? The next logical step is to use the vision and language feature backbones, the data frames we put together. We have to stitch them nicely to form a data set, right? And this is where we are, and the three things, the important thing that you want to notice is what are the three things that we pass into the model, which is the image embedding, which is the embedding of the movie poster, the JSON files, and the plot embedding, which is the textual modality of the plot line of the movie. And then we are also additionally sending one more variable, which is the title embedding, the movie title embedding, and then obviously the labels, right? The next couple of cells are basically using the class we put together to actually generate the Torch dataset itself, and then coming up with the data loaders for training and validation, and we are setting the batch size. Those are pretty straightforward, and I'm not going to go through that. And then the next step is the PyTorch training loop for training this multi-label classification task. One of the main things you want to notice is we are using an appropriate loss function. The variables that we are passing are coming in. That is the image embedding, plot embedding, and the title embedding. We got 23 labels. What else? This is pretty much a straightforward, simple PyTorch training loop. There is nothing different or novel here. I would request you to go through that. As usual, I'm saving all the important checkpoints. That's pretty much it as far as the training loop is concerned. Let's move on to the next logical step. The next two, 6a and 6b, are two important logical steps where actually we are trying to show the networks that we are trying to train here. We want to obviously show how a vanilla fusion network performs on this data set, and also try to contrast that with the gated fusion network, right? So the first cell you are seeing here is, like we saw in the previous episode, we are just taking the image and text modalities, and then we are just simply doing an element wise product and then passing it on to a fully connected layer, do some batch normalization dropout, and passing on to the final classifier layer. The only thing you would notice differently is as far as the text modality is concerned, we have two variables. One is the plot and the title. We are just doing an element wise addition to form the text feature, and then the vision feature is as is, and this is where we are doing the element wise multiplication. There is nothing different from what we have done from the previous episode. This is like this is why we call it as a vanilla fusion, right? Then the next one is important, right? The gated fusion version of the network, right? An important thing I want to notice is the gated fusion architecture is not something, like I said, it is not something we are introducing. It is it's pretty much the thing that I'm highlighting here is actually a snippet from the paper. We are basically implementing the gated fusion architecture recommended in this paper. I'll give you a link to the paper. As you can see that they are basically recommending a weighted interaction, an element wise product of weighted interaction of both the vision and text modalities with the sigmoid nonlinearity as a gate for either of the modalities, depending on how you want to do it. As you can see, they are clearly saying where you want to apply the sigmoid nonlinearity as a gate is a hyperparameter. It can be done on the vision or it can be done on the text, right? So let's see how we're implementing that. We are just borrowing the vanilla network from the previous cell, but we are making some small changes, right? We are making it as a rather than a simple interaction, it's a weighted interaction. So we can see that there are one parameter or one weight per modality, right? The other thing that you can notice is we are applying the gate on one of the modalities. The modality of our choice is the text modality, right? So that in summary, what you have done is we have made it as a weighted interaction for both the modalities, and plus there is a gate. Pretty much except for this, everything is same, right? So now we have a vanilla network, a vanilla fusion network, and a gated fusion network. Now let's try to train these two networks and see how they fare. The next logical step is to initialize the respective models and go on about training the individual models, right? There will be some obligatory cells and obligatory code in between, which I'm not going to get into. When you have access to the notebook, please check it out, right? So cells 7a and 7b comprise the training loop as well as the training history for the respective models, right? So we are not going to run the actual training as it's going to take some time. I would request you to look at the training progress, how the losses are progressing, how is the fitting graph looking, when is the early stopping kicking in, and all these things. These are pretty straightforward, and I'll leave it to you guys. In fact, I'm going to cut to the chase and show you the results of the model's performance. So usually what we do is we show the training portion, and then we show the inference performance of the best models on the test data, and then do some analysis, and then actually present the results. For now, I'm going to do it slightly differently. I'm going to go ahead and present the results first, and then we can do the analysis later, and you will know shortly why we're going to do that way, right? So obviously the inference has been run by picking the best models for each of the network and the test data, right? I'm going to present the results first. As you can see, the first section of the result has the performance of our vanilla fusion network and our gated fusion network, and as you can see, our gated fusion network definitely seemed to have an edge and definitely outperforms the vanilla fusion. That's the first takeaway. Does the gated fusion network has an advantage over vanilla fusion or not? I think we have answered the question, especially if you look at the F1 macro, which is very relevant for F1 macro and F1 weighted, which are kind of relevant for multi-label tasks, right? F1 macro is about 9 percentage points, and the other things were about 5 and 6 percentage points, right? So those are pretty good. Since this is one of the hardest multimodal challenges or data sets, it also makes sense to compare it with the current state of the art, right? So let's go ahead and look at the current state of the art. As you can see, if you look at the current state of the art, especially the best performance of the current state of the art is beaten by both our vanilla fusion and gated fusion. The gated fusion absolutely smokes the current state of the art, but some of you guys may argue that it's not an apples to apples comparison, because the current state of the art was slightly older and it was using a slightly older feature backbones. Fair enough, but we are answering two questions here. One is, does the gated fusion network pays off when compared to vanilla fusion network, given the fact that the feature backbones are all same? So that is something we have answered, and also we have to demonstrate. It is an obligatory thing to demonstrate that this is a hard problem all along. Even the current state of the art in the past has struggled to perform on this data set. There is also another state of the art. You can look at the score. So summarily, we have beaten both the state of the arts using our vanilla fusion itself, and our gated fusion is paying off. So that's the result we wanted to present first, and the next step is the actual analysis of the results, right? So when you run the classification reports for the respective models, that is the vanilla fusion network and the gated fusion network, these are the respective numbers, and feel free to analyze the performance of the individual models on the respective genres and figure out what are the advantages of individual models, what are the blind spots. The two analysis you want to do is how the vanilla fusion network is faring, what are its blind spots, how the gated fusion network is faring compared to the vanilla fusion network, and another thing you want to do is how do you improve the gated fusion network further, right? That's one of the main exercise I'm leaving here. Analyze the gated fusion model and figure out what are the labels the model is confused about, and how you can improve the model's performance by doing better feature engineering and so on and so forth. That's exercise number one, right? So another interesting thing is I wanted to understand the activations of the gate which is surrounding the text modality. So what is the intent behind understanding the activation of this gate, right? So what we want to understand is for a given movie, how does the gate activate or does not activate, right? How do you understand how the gate is performing across movies or across samples? So for making this analysis, I took some random 5000 movies as samples from the test data set and ran this. I'm very sorry guys, this graph is too big to fit into the screen. Once you get access to the notebook, feel free to refer the graph as you watch the video. So I will just explain how to interpret this graph because it is important. Right, this graph basically shows for what percentage of the movies the text signal contributed in predicting a particular genre, right? Not necessarily the correct genre, right? So what do I mean by that? Let's take an example, right? So for film noir, the gate has been activated 97% of the time. That means out of all the samples that belongs to film noir, 97% of the, for 97% of the samples, that the gate has been activated. That means the text modality has contributed in predicting the genre, not necessarily the correct genre, right? It could have been wrong also. So we are just trying to capture the contribution of text modality based on the gate activation. That's the intent of this analysis, and this graph is depicting that, right? And intentionally I have skipped the code which basically traces the activation signals. Feel free to figure it out. That's another important exercise you might want to get your hands on, right? The another important aspect of which is related to the tracing the activation itself is you can also look at the distribution of the movie plot length when the gates are activated, right? When the gates are activated, the text modality is paid attention to. When the gates are not activated, the text modality is not paid attention to. That means only the vision modality is paid attention to. As you can see, when the gate is activated and when the gate is not activated, as you can see and compare the distribution of the text length, when the gate is activated, the text length is a lot more denser and longer for the plot length. And obviously the text was not so significant when the gate was not activated, right? That's an interesting observation related to tracing the signals of the gating mechanism. The other exercise I would like you guys to do is, now that you have done, you have already done the result analysis and already done an exercise on figuring out the tracing code. The last part is to further improvise the gated fusion network. You could look at it in different aspects. A is to try different combinations of feature backbones, or B is to do better feature engineering in terms of, let's say, feature like year of the release or the language code of the movies, and or use maxword MLP as opposed to vanilla MLP, and try to see if we can squeeze another 2 to 3% on top of the gated fusion network. That will be awesome. All right, let's close this episode with some closing thoughts. I wanted to quickly review the couple of answers people have given. So as you can see, most of the answers were focusing on or assuming that the data set is not existing, and they were, which is a fair assumption, and they were trying to give some answers as to how do we label the data. And also they have given the idea as to how to label, and then once labeling is done, how do you go about mapping the movies to the respective tags. The first answer, as you can see in the screenshot, what I love about it is, as far as labeling is concerned, they are resorting to multi-label zero-shot classifier. I believe they have the Hugging Face implementation in their mind, which basically reframes the NLI task, which is a pretty good answer. But the problem with the approach after labeling is to use, they are basically suggesting that they'll have to use the script as the text modality to label the movies, which can be a problem because for once the scripts are not standardized. The movies we have in this data set range from 1890s to up until 2020. So it's pretty hard to get the key scenes and apply the multi-label zero-shot classifier on top of that. The second answer, the challenge is the same again. They're talking about labeling the data set, and they're suggesting that they will use sentence transformers for the labels, sentence transformer on the labels and the text to get the respective embeddings, and then they will calculate cosine distance. That is that is wrong. That's not how that won't work at all. And as a matter of fact, I want to talk about all things. I want to talk about small things like this in another series, because the vision language modeling series is having a specific curriculum. I don't want to diverge into different topics. So I want to dedicate a short series like 10 to 15 minutes called Stuff You Should Know in Applied ML. So I'm basically soft launching the series here in this episode. I would like to cover these kind of minor things in that series. Right? So that's one thing. The other thing is I wanted to give you guys a sneak peek to what is coming in the future episodes. So for those who are thinking that we are only looking at discriminative tasks, don't worry, we will eventually graduate into learning joint embeddings for vision language modalities and do some search retrieval. For instance, look at multimodal queries. In e-commerce case, if you give an image as well as some kind of text, you will have to retrieve the images based on the combination, right? So it's a very popular use case in e-commerce, right? For example, you want a T-shirt, but you don't want in that color or you don't want in that style. How do you go about do that? And then there is content-based image retrieval and things like that. And as far as generative model is concerned, I can tell you that we will do some version of a controlled image captioning. We all know that there is a standard image captioning task, takes an image as an input and then generates a caption. But what if we want to control the captioning process by passing an image as well as some kind of control tokens? So that's where the control captioning comes in, and we will cover that as a part of our generative models. We will also cover some advanced versions of VQA where we need not just the plain image features, that's a global image feature, but also local features like regions and objects. I will also demonstrate where unimodal pre-training with custom fusion can beat multimodal pre-training in the coming episodes, right? And that's pretty much in terms of what I want to cover in the future episodes. The answers to the exercise will be shared in the Slack channel. As far as the winners, 5 lucky participants will get a laptop stickers, and then there is a book giveaway we planned along with the authors. 2 of the best solutions for the exercise will stand a chance to win a brand new copy of the GPT-3 book signed by the authors. The image preview of the book cover is shown just below. So that's pretty much what we wanted to cover in this episode, guys. Thanks for your time. I will see you guys in another episode.